Great. So I first want to apologize for the inconvenience during the FOM, where we had some technical issues with the presentation, but I hope that I can guide you through now. Well, we are always happy to answer your questions. Unfortunately, this is not live now, but always feel free to reach out to us via phone or email or whatever. We are always happy to discuss your questions and your inquiries. So first of all, the topic of this talk is chip-based technologies that we develop for precise control on the one side of sample temperature, but on the other side of the illumination conditions, specifically tailored for high resolution and single molecule imaging studies. Interference itself is a startup founded back in 2020. We are located in the northern part of Bavaria in Erlangen. And the idea of what we do is that we want to enable basically everyone to exploit high sensitivity microscopy to study under very reproducible and quantitative conditions, complex biological systems. And the devices that we developed that should allow this are designed in a way that they're simple to use and plug and play and can be added to any already existing setup. For this, we exploit thin film technologies in combination with micro and nano fabrication to generate some highly sensitive sensor systems that are in direct touch with the sample volume and that then sense or excite, for example, the sample volume. For this, we rely on standard microfabrication techniques in the clean room. This is from the chip technology or microchip fabrication side, the standard technologies that we use there. The chips itself that we fabricate are then done in the clean room on wafer scale, and then cut into dies and supplied to our customers. As we currently foresee in high resolution microscopy, there are 4 pain points that are summarized on this slide. On the one side, there are three parts which connect to hardware issues, and one part on the right side, large amount of emission data, that is a software related issue. The 3 hardware points are temperature control. It's quite difficult in common setups to control precisely temperature. For high resolution, super resolution studies, you always require high NA objectives. This comes with its own drawbacks, and the setups itself are quite complicated, include highly sensitive optics. And those 3 points lead to often undefined measurement conditions that might be different from day to day, but also from setup to setup or from lab to lab. You have a limited field of view. The systems are high maintenance. You require very skilled personnel to maintain the complicated setups, and that results usually in high maintenance costs that you have. Our products try to tackle these first 3 hardware-related issues. The VAHIT system is explicitly solves the issue that you have with unreproducible temperature conditions in your sample volume. When you wonder why temperature is interesting in most biological systems, you can read our freshly published Microscopy Today white paper. You can download it by just following this QR code or searching for it. And there we summarize issues that might arise during imaging that can affect your actual sample temperature, and also processes that are temperature dependent. If you think about temperature dependent processes that can happen inside inside your field of view or sample volume, there's a huge variety of physical reasons which are physical processes that are actually temperature dependent. A few of them are summarized here. On the one side, you have the particle diffusion that is linear dependent on the temperature, but also the speed of chemical reactions can be or is typically temperature dependent, and the easiest or simplest empirical description, this follows the Arrhenius equation as described here. On the other hand, you can have very sharp temperature dependencies as in phase transitions. If you think about melting of crystals, crystallization or evaporation processes, but there are also different types of phase transitions that can happen as, for example, folding or unfolding mechanism of proteins or DNA hybridization, for example. Further than that, there's thermal expansion, which can affect your observation that you do if you do temperature dependent measurements, and this is also often causing issues actually in your measurement. In general, one can say that temperature can have a very strong impact on living cells, on biosensors and polymers, proteins, and any nanoparticles that you might want to observe as a function of time in dynamic behavior. There, temperature is a crucial element that can determine function as well as dynamics. There are several external factors that can affect your sample temperature. One effect is evaporation. So due to evaporation, the concentration in the sample volume can change over time. You can have condensation, but also evaporative cooling can heavily affect your sample temperature just because you have water as a medium that evaporates over time and that cools down the sample volume itself. You can have thermal drifts that move your sample, although you might not want to move it due to different thermal expansion coefficients of your sample stage, for example. Typically, you have a limited temperature range and a limited temperature dynamics with common systems. You can at maximum reach like 40-50 degrees C. And the control of the temperature is quite complex and usually often requires external calibration, because if you're only interested in the exact sample temperature, but often this temperature is not measured there, it's measured somewhere else, and that's why many of the effects that can affect the temperature are not considered in these setups and require additional calibration. There are some graphs summarizing this effect here. So this graph shows the evaporative cooling that you have. So if the set point is, although the set point might be 37 degrees C and the temperature inside your incubation chamber is 37 degrees C, due to evaporative cooling, the sample temperature might be only 33 degrees C. But also the objective can act as heat sink if you put it in contact with the immersion oil to your sample. And all these things can lead to an undefined temperature in your field of view. That's why we've said we want to come up with a very simple solution that directly measures the temperature inside your sample volume independently of your actual experimental setup. And that's the Vahid. The Vahid system integrates on a cover slip a restricted heated area and an integrated temperature sensor that is in direct thermal contact with your sample volume. This chip that you see here is mounted in a microscope adapter. It's hooked up to the control unit that reads out and controls the temperature, and the sample is then mounted directly in that kind of reservoir that you see here on that chip. This chip is sitting in this microscope adapter and hooked up then to your microscope. The microscope adapter itself has a footprint of a standard microscope slide, so you can basically put it onto any microscope. The thing itself stays at room temperature. This limits the drift, and the connector here connects electrically the substrate to the control unit. The substrate itself are the important part of the device. The image is shown here. So these are the cover slips with integrated sensors that have a 5 by 5 millimeters heated area and a tiny temperature probe integrated in that field of view. And this allows you now to, with direct feedback, set the temperature to any arbitrary value that you would like to have it without affecting the imaging quality. The substrate itself are multi-use disposable, so you can reuse them and clean them, but at a certain time they might get destroyed. The technical performance of the system was quite important to us. So on the one side, it's very precise, so you can stabilize the temperature to a very high degree. As you see here, it's a time trace where the temperature stabilized to 37 degrees C, and we achieve standard deviation below 0.01 degrees C over an extended period of time. So in principle, the system, due to its fast thermal response, is similar to a thermocycler for super resolution microscopy. The fast thermal response is shown here. So the blue is the set point and the red curve is the actual sample temperature. And you can then program arbitrary temperature profiles, and the sample volume follows accordingly. With that, you can achieve temperature changes up to 100 Kelvin per second. And well, the precision and the simple easiness to use is actually what people appreciate about the system. But also it's meant for high resolution studies. So we characterized and paid a lot of attention to optical performance this system can achieve. And this is summarized here, which shows using a 100x 1.49 oil immersion objective, the point spread function as function of temperature is not affected by the Vahid system. Up to 80 degrees C, the point spread function in lateral direction stays diffraction limited. Above that, it's widened slightly, but this is due to the effect of the nanoparticles that we are tracking that start to diffuse at those temperatures. So this is so far the Vahid system, which tackles temperature control. But let me switch gears and talk about high-NA objectives and complicated setups. And that's where where the QSight system is now trying to solve those two issues. QSight system is a turf add-on basically for any microscope that relies on integrated optics and exploits waveguides to optically excite in turf manner the sample volume. As you know, turf is a great technique to generate very high signal-to-noise ratios for single-molecule studies and super-resolution microscopy. But this technique itself comes with several drawbacks. And these drawbacks include that you always require immersion medium in objective-based approaches to achieve the required numerical aperture of 1.4 that is needed to have the beam entering in the total internal reflection condition. This comes with a drawback that you have only very small field of views of 60 by 60 or 100 by 100 micrometers. The systems often require high maintenance. They are temperature sensitive. By changing the temperature, you might lose your turf angle. The penetration depth usually needs to be calibrated if you want to do quantitative turf. You suffer often from inhomogeneous field distributions and poor polarization purity. And we think that these drawbacks limit the range of use for turf microscopy. And that's what we want to solve or unlock. With these approaches, it's often difficult to perform quantitative and reproducible turf measurements because it requires well-trained staff that takes care of these setups and calibrates them and just maintains them. We don't do objective-based turf. Objective-based turf is great, but as said, it has its drawbacks. So what we do is we, instead of sending the beam into an objective and then exciting locally a small area of the sample that is shown here, we exploit a thin film waveguide that is sitting on top of a glass chip that supports a guided mode. And that guided mode has a strong evanescent field tail entering into the sample volume. So when there's now a cell culture sitting on top of the waveguide and there's an optical node launched into that thin film, the cell culture feels the evanescent field of the waveguide and can start progress everywhere where the waveguide is. And now you in principle decouple the excitation completely from the detection. And you can now detect with any objective, which is not necessarily an oil objective, but a low magnification objective, and capture very large field of views that not only image one cell, but now, like, let's say, multiple of cells. You can image now in the range of square millimeters. And this is what QSight is doing differently. So we think by that approach, we not only decouple fundamentally the excitation from detection, but we also use a semi-monolithic structure where the excitation optics is basically engraved in the glass chip. And this allows for very reproducible measurement conditions. And this in combination not only allows to improve on the already existing benefits of turf microscopy due to the very efficient excitation and no backscattering losses in the objective or high low residuals, we have even higher signal-to-noise ratio, even lower phototoxicity, but simultaneously improve on all the shortcomings of turf. So you can now use any objective. It's ultra-wide field of view, low maintenance, temperature insensitive, well-defined penetration depth, flat illumination profile, and you generate a high polarization purity. And the system is plug and play. We like to call it space-proof system. So that's a typical field of view where you have a single cell. If you illuminate in standard TÜV, objective-based TÜV, but that's what your horizon when you excite via QSight. The system itself is comprised out of 4 components. So you have a control unit that hosts light sources and electronics. You have a light coupling module that ensures light coupling into the waveguide chip. You have the waveguide chip itself that you see here that is mounted on a microscope adapter that can be actually put onto any translation stage of your microscope. That's how you can equip every microscope with TÜV capability with a simple add-on without changing any optics. Here we summarize again all the benefits of the QSight system. Field of view, any system can be upgraded. Superb signal to noise ratio. We have calibrated intensity. It's plug and play. Highly homogeneous illumination profile, and we have up to 6 light sources in the visible. So if you're interested in QSight or Vahid, let us know. We are happy to discuss the requirements. QSight will be launched mid of this year. Vahid is available on a short notice. Just reach out to us and discuss your application. Thanks for your attention.